Hello everyone, my name is Sam Dow. During the last 1 year or so, I had the privileges of involved in developing the battery component libraries in MapleSim. And in my presentation today, I would like to brief you about what Maplesoft has to offer in terms of regarding battery solutions. Batteries are getting more and more important in our life, so we can virtually find the uses of battery in any applications. For example, we can find batteries, uses of battery in medical devices, robotics, nuclear power plant, electric vehicle or cars. A lot of companies and research laboratories are putting a lot of money in to finding new type of material to address the current limitations of battery. For example, the low energy density of battery or the poor thermal stability of batteries. Alongside with that, there are also efforts in developing high fidelity models of electrochemical cells that can accurately provide a good estimate of the behaviors of battery in order to allow the users or researchers to test different designs or different configurations of battery pack or physical systems that are powered by batteries. And there are also the needs to develop fast models of batteries that allows the users to evaluate the performance of new designs or new configurations for a large system, for example, a very large battery packs. And a good battery model also allows users to have access to system level equations that can provide further insight of the physical behaviors of batteries. So in MapleSim Battery Component Library, we use two different approaches for modeling a battery, namely the equivalent circuit approach and electrochemical approach. And I'm going to get into the details of each of these approach in a moment. So the equivalent circuit approach represents the battery behavior by using an electrical circuit. So basically, by using the electrical components such as the capacitors, resistors, or inductor to model the physical behavior of a battery. The advantages of this approach that conceptually the models developed based on the equivalent circuit approach are conceptually simple. So an engineer doesn't need to have a background of electrochemistry in order to understand the behavior of an electrical circuit. And this type of model are also very easy to validate as well, because the behavior of the equivalent circuit battery models are based on a small set of configuration parameters that can be adjusted very easily. The second approach, which is the electrochemical approach, produces more accurate models for a wide range of applied current. So this type of models, the electrochemical battery models, are based on a large set of physical configuration parameters and complex partial differential equations, which I will get into more detailed in the next few slides. So let's take a look into the internal structure of a battery model that is based on equivalent circuit approach. So this the model that you're seeing here is a model is the internal structure for a lithium polymer battery. So you can see that there are two linear circuits. The linear circuit on the right hand side consists of a series resistor and two RC circuits that allows the model to describe the instantaneous and short time transient and long time transient response of the battery. The parameter of the electric components, for example, the variable resistors and capacitors here, are determined by a MapleSim custom component block in the middle. and their values are determined by a bunch of by a set of equations inside this custom component, which describes the relationship of the parameter of the linear circuit on the right hand side based on the state of charge of the battery, which is measured by using a voltage sensor based on a large capacitor on the linear circuit on the left hand side. So the large capacitor on the linear circuit on the left hand side allows us to model the capacity of the battery. So what you see on the screen now is a snapshot of a battery model in MapleSim. So on the left hand side you see this is a palette that consists of the battery components in MapleSim. The equivalent circuit battery models are inside this red rectangle. So you can see that we have the equivalent circuit battery model for lead acid, lithium ion, nickel metal hydride, and we also have some other user-defined battery components as well that allows the user to curve fit those components based on experiment data. The behaviors of the equivalent circuit battery models are described by a small set of parameters that can be seen inside the rectangle on the right hand side here. For the lithium-ion battery, we can also select different kind of cathode and anode material. So for example, we have 12 different types of cathode material for lithium chemistry, and we also have two different types of material for lithium chemistry as well. So in theory, we can have 24 different combinations of lithium-ion batteries. On the other hand, the electrochemical approach to battery modeling describes all the details of physics that happens inside the battery, including the two chemical reactions that you see on the screen right now. So for example, this is the anatomy of a lithium-ion battery, and the description of this is based on the so-called porous electrode theory proposed by Professor John Newman at the University of California in Berkeley. So for this type of battery model, the battery model is described by as having a porous cathode, porous separator, and porous anode. So the lithium, during charge and discharge processes, the lithium ion can go back and forth between the two electrodes. So that's why this kind of model is also called the rocking chair model. So this type of battery model looks into every details of what's happening inside the battery. For example, the partial differential equations that you see here describes the mass transport or the concentration of lithium ion on the solid phase and the concentration of lithium ion in the electrolyte phase. So the mass transport of the lithium ion are described by these two partial differential equations, and we can also describe the concentration, the distribution of electrical potential in solid and electrolyte phase using these two partial differential equations as well. And all of these variables are related by an algebraic expression which is called the Butler-Formel equations. So this is an exponential function which is described by the parameter k, which is a chemical reaction, the concentration of lithium ion on the surface, and the other variables that are coming from the other partial differential equations as well. The electrochemical battery model also incorporates the open circuit voltage equations, which are curve-fitted based on experiment data. For example, the top equation is the open circuit voltage for lithium cobalt oxide material, and the second equation is the open circuit potential for the graphite anode. And both of these equations are the function of theta p and theta n, which is basically the state of charge of the cathode and anode. So for each material, we actually curved the open circuit voltage equation for different type of material and incorporate them with the electrochemical battery models in MapleSim. The electrochemical battery model also has the equations that describes the thermal effects for the battery. For example, the differential equations that we see here describes the thermal balance between the reversible and irreversible thermal processes that are happening inside the battery. And to address the effects of different type of material on the thermal performance for the battery, we also covered the entropy of reaction equations for each material based on the available data that we found in the literature. For example, the two equations that you're seeing here are the two equations that describe the entropies of reaction for lithium cobalt oxide and the graphite anode. So in MapleSim, the electrochemical battery model consists of two components. The first component is for nickel metal hydride battery, and the second component is for lithium-ion battery. So the behaviors of the electrochemical battery models are described by a large set of parameters. So if you take a look on to the list of parameters that we have on the right hand side of your screen now, you can see that we have a parameter that allows you to define the number of cells that are connected in series in the battery pack. You can also define the minimum and maximum state of charge, which would define the terminate condition for the simulation. You can also define the capacity of the battery in amp hour, internal resistance, and other electrochemical parameters for the battery. For the lithium-ion battery, you can also select among 12 different types of material for the anode, for the cathode, and 2 different types of material for the anode for the lithium-ion battery. For example, some of the materials include lithium cobalt oxide, lithium iron phosphate, lithium manganese oxide, and some of the other newer materials. And for the anode, you can also select between the graphite anode or lithium titanate anode. So these materials basically cover most of the commercially available lithium-ion battery materials on the market. So this is an example of simulation results for the battery component in MapleSim. So the graphs that you see on the left hand side describes the voltage curve of a small battery pack consisting of 4 lithium-ion cells being discharged by a pulse current. So you can see when the current is turned on, the battery is depleted and the voltage is going down. And when we turn off the current, then the voltage will recover to the open circuit voltage. And this type of model also simulates the transient from one voltage value to another voltage value very well. And the plot on the right hand side shows the voltage curve for lithium-ion battery versus different types of cathode material. So we can see the voltage curve for lithium cobalt oxide, lithium manganese oxide, lithium iron phosphate, and other materials as well. And we can, and the electrochemical battery model can also capture the thermal effect of a battery very well. And the example simulation results here shows the rise in the temperature in a lithium-ion battery with lithium cobalt dioxide cathode being discharged by a constant current. So by changing the parameter H, which is the effective heat transfer coefficient, we can see that when H is 0, which is corresponding to the adiabatic process, the temperature is rising very quickly, and when H is getting larger, then the battery is being air cooled more efficiently. So you can see that the temperature is increasing more slowly when H equals to 1000. And we can also simulate the thermal behavior of the battery versus different charge and discharge current as well. So when we use a higher current, the temperature of the battery is rising very quickly, and when we use a lower discharge current, the temperature of the battery is rising more slowly. And we can also capture the thermal behavior of the battery versus different type of cathode and anode material as well. The green curve that you see here is corresponding to the temperature rise in a lithium-ion battery with lithium cobalt oxide cathode, and the red and the blue curves are for the temperature curves for the battery with lithium manganese oxide and lithium iron phosphate cathode. So you can see that very clearly from the plots here. The lithium cobalt oxide cathode has much poorer thermal stability compared to the other type of materials. So that's the reason why lithium manganese oxide and lithium iron phosphate are getting more popular for automotive application because of their good thermal stability. The parameters identification tool is also part of the battery component library in MapleSim. So if you have the test data for the battery, you can bring them into MapleSim and then use the parameters identification tool to identify the parameters of the battery model based on the experiment data that you have. The graphs that you see on the right hand side here shows the curve fitting result for the lithium-ion battery with lithium cobalt oxide cathode based on two different set of experiment data which are obtained by discharging a real battery by using two different current. The table on the left hand side shows the parameter after curve fitting. So you can see that the capacity of the battery is 2.447 amp-hour, and you can also see the other parameters including the thickness of cathode, thickness of anode, and the other parameters being identified as well. Modeling the life or the state of health of the battery is also a very important part of battery modeling and simulation. And in the battery component library, we also include an example which shows how you can model the life or the degradation of the lithium-ion battery versus the charge and discharge cycles. So the state of health or the degradation of the battery is believed to be caused by the formation of the so-called SEI layer. So SEI stands for solid electrolyte interface layer. So this layer is formed on the anode of the battery during the charge process. So the formation of the SEI film or layer is described by this differential equation. So delta is the thickness of the SEI layer, and so this differential equation describes the formation of the SEI layer over time, and it is dependent on some parameters including J, which is the lithium ion flux due to the SEI film formation on the anode during the charge process, and the other parameters including the area and the density of the SEI layer as well. And J is described by this algebraic expression, which is dependent on the reaction rate, area, concentration of the electrolyte, and the other and diffusion coefficient. So the diffusion coefficient D is also dependent on temperature, and it is described by using Arrhenius equations. On this slide, you can notice the component on the left hand side here describes the the degradation of the lithium-ion battery, and it takes three inputs, which is a discharge current, the temperature of the battery, which is coming from the lithium-ion block in green color on the left-hand side. I'm sorry, on the right-hand side, and the state of charge of the battery. So the state of charge of the battery is then used to calculate the depth of discharge of the battery as well, and it is fed into the component, the degradation component. So this is a MapleSim custom component which consists of the equations that describes the degradation of the battery or formation of the SCI layer depending on the applied current, thermal, and depth of discharge. The two outputs of this block are the internal resistance of the battery, which is caused by the formation of the SCI layer, and the state of health of the battery. The parameters that are used to describe the life model of the battery can be entered numerically, or they can be entered symbolically, allow this model to be curve-fitted if you have experiment data for the battery degradation. So now let's take a look into some simulation results for some of the models that are based on the battery component in MapleSim. So the simulation results that you're seeing here is for the life model of a single cell lithium-ion battery. So this battery is being cycled by using constant current. So for the discharge process, the applied current is minus 30 amp, and for the charge process, the applied current is 30 amp, and the current is turned on. It's switched between the charge and discharge process depending on the state of charge of the battery. So we can see that so this model has a predefined depth discharge of 90%. So whenever the state of charge of the battery reaches 10% level, it will be charged up again to full and then discharged. So the total number of cycles for this simulation is about 6 cycles, and you can see the growth of the internal resistance due to the SCI layer, the state of health of the battery, the fluctuation of the temperature, and also the thickness of the SCI layer as well after 6 cycles. So this is a second model that demonstrates the use of the battery component library with state of health. So the model that you see here is for an electric vehicle with battery state of health, and we can see some of the parameters of the vehicle in the column on the left hand side, and the battery parameters on the right hand side. So we have 99 lithium-ion cells, and the capacity for the battery pack is 100 amp hour, and we use lithium cobalt oxide and graphite for cathode anode chemistries. So we use the EPA drive cycle to evaluate the performance of the battery pack. So the first plot shows the velocity of the vehicle, which is overlapping with the speed in the drive cycle. The second plot is the battery state of charge, which is dropped to about 77% from 80%. And you can also see battery voltage, battery current, temperature on the battery, the thickness of the SCI layer, state of health of the battery, which is drops us a little bit because we're using a very short drive cycle. And you can also see the SCI film resistance on the last plot as well. So to sum up, the battery component library are described by using Modelica modeling language. So a causal modeling approach for the battery allows the physics laws to be embedded with the battery components. So for the battery component in MapleSim, you don't have to worry about the equations inside each component. You can actually view the equation by using the Modelica code view capability in MapleSim. And this approach also allows the battery component to easily be easily integrated with the other components from the different physical domains in MapleSim. So you can easily connect your battery component with the other electrical components in MapleSim. You can also connect them to the other thermal component, as you can see in the model diagram on the right hand side here. So these are some of the typical applications of the battery component library in MapleSim. So the battery component libraries are perfect for automotive applications. The examples that you see here is for an electric off-road vehicle, which is powered by a lead-acid battery pack. And we can also use the battery component library for EV HV application as well. And the screenshots that you see here is for a series HEV model with a cooling system. And they can also be used for smart grid design or power industry. And also hardware in the loop is also a very important applications that you can do with the MapleSim battery component library. So the screenshots that you see here is for a very large lithium-ion battery pack consisting of 144 cells that we created for one of our clients. So even with the large size of this battery pack, this the model is still be able to simulate much faster than real time, far exceeding the expectation of our customers. Battery degradation is also it is also part of the battery component library. All of the battery components in MapleSim Battery Library has a capacity input that allows the user to incorporate or develop their own algorithm to describe the life model of the battery very easily. And because because the battery components in MapleSim are very efficiently described, and they're also based on very fast code as well, they are very suitable for optimization processes. So the optimization processes usually require the same model to be executed thousands of times in thousands of iterations. And the battery component in MapleSim Battery Library are very suitable for optimization purposes. And we can use this the MapleSim Battery Component Library for testing different configuration or different designs of some mobile devices, and also testing and developing battery management systems as well.